Hi, my name is Kirk Vodopals. I'm a hydrologist for Mendocino Redwood Company. I'm going to start off my presentation with a little outline here. First, we're going to go through a little background of Mendocino Redwood Company. Then we're going to go into the subject of our road network and get into some specifics of restoration, some of the tools that we use in those restoration projects, and some of our fish passage issues, and then end with some of our monitoring programs. So, Mendocino Redwood Company was formed in 1998 on former Louisiana Pacific lands. It's approximately 220,000 acres. We employ roughly 45 full and part-time staff. We have our own road department with our own heavy equipment, and we spend roughly $1 million annually on roads. Since 1998, Mendocino Redwood Company has decommissioned over 112 miles of roads. Historic roads, which are no longer in use, account for about another 18.1 miles, and decommissioned and historic roads represent about 6% of the Mendocino Redwood Company road network. Some of the issues on our ownership include fish passage barriers. We fixed most of the low-hanging fruit already. Other issues include sediment-impaired watersheds. Most of our watersheds that's in the ownership are listed as impaired for sediment and or temperature. We have lots of old roads and skid trails on very steep topography out here, and mainly in Mendocino and northern Sonoma County. So timber harvest does fluctuate annually, and that means that the amount of road work that we get done fluctuates. In order to plan and manage for harvesting and road work, we've developed a draft habitat conservation plan and the state equivalent natural communities conservation plan. Been working on that for over 10 years, and we're hoping to be done very soon. Mendocino Redwood Company owns and manages about 2,300 miles of truck roads. It does not include skid trails. That's the equivalent of a road density of about 6.9 miles of road per square mile of ownership. We have close to 5,000 culverts and counting. And one of our conservation-related goals outlined in our habitat conservation plan is to reduce the percentage of seasonal roads and convert them to temporary roads. This means taking out permanent drainage structures such as culverts, and replacing them with low-maintenance facilities such as fords or natural channels. Road maintenance is a major issue, specifically one of those issues being road brushing, maintaining the flow of traffic on roads. We deal with that by mounting a brush head on an excavator or a bobcat. Rock is another major issue. The rock supply is limited. Buying rock on the outside market can be very expensive. We do have our own rock pits, but the quality is highly variable. The supply within those rock pits is highly variable, and then developing a usable crushed rock is. We're exploring the use of geotextiles and other technologies, which I'll get into, and we follow our guidelines developed in our habitat conservation plan, specifically Appendix E is one of our other ways of dealing with our road network. Here's some examples from our habitat conservation plan as they pertain to roads. In flood-prone zones, in Class 1 aquatic management zones, which are basically alluvial flats where rivers can meander. We don't have very many of those, but any road construction is excluded from these areas, including all equipment use, unless there's an existing road for use in road decommissioning. So we're really trying to stay out of those areas. New road construction within riparian areas trying to ensure that the road does not parallel a watercourse for a significant distance to minimize erosion and minimize the approaches of a watercourse crossing in these areas. We have a road inventory monitoring program. It's designed to collect GPS coordinates of our entire road network at specific sites and road segments. These sites include culverts, crossings, landings, erosion sites, spoil piles, water holes, road slides, and gates, as well as the road network itself, the linear features. We aim to resurvey the entire road system, including all these features, every 10 years. I want to note that this road inventory monitoring program does not collect data specifically for the intent of repairing or restoring the site or the road segment, but we do use the information when planning for a restoration project. Monitoring for sensitive resources related to roads we have an extensive program for that. Here's some of the examples of these sensitive resources. Rocky outcrops, a very small portion of the ownership. A much larger portion are these uncommon natural communities. Forest, for example, there's no timber harvesting and minimal road construction allowed. Likewise, there will be no timber harvest in oak woodlands, and we will only conduct essential timber harvesting in conifer stands that border oak woodlands. Rare plant monitoring is broken down into 4 categories with specific conservation measures in each category. Examples of conservation measures include communicating location of the rare plant species to field personnel, specifically to heavy equipment operators and herbicide applicators. We also install long-term marking systems such as painted T-posts. We GPS the sites, try to avoid altering the hydrologic conditions, and we apply buffers and restrict operations within rare plant areas. Other sensitive areas include potential and existing red-legged frog habitat, such as wetlands, wet meadows, and wet areas. We have equipment exclusion zones for these areas and measures to avoid artificial wetlands. Conservation measures for seeps and strings where other aquatic sources can exist. This includes protections of these seeps and springs within riparian zone boundaries, as well as extending those riparian boundaries to encompass those seeps and springs that are nearby. And we have equipment exclusion zones in these areas too. Another obvious sensitive resource is spotted owls. Noise disturbance can occur from timber management, so basically we try and stay out of their areas during breeding seasons. We have an extensive monitoring program for territories and potential habitat. And basically we just set up buffers to avoid disturbance. Marbled murrelets and point arena mountain beavers are other sensitive species that are affected by road construction, road maintenance. We do operate and maintain our own radar truck for monitoring marbled murrelets. One of the products that we use to maintain our roads includes a road enzyme. We're just starting to experiment with this product. It improves dust abatement in the summertime. It's basically, we're trying to minimize the amount of fine sediment that's created from a heavy amount of log haul traffic in the summertime that deteriorates the road surface. So we apply this road enzyme, and it seals up that road surface and potentially has the ability to hold together that road surface for longer than a season and actually turn fairly not so solid road into a firm road surface that can be traveled on multiple seasons. It works well in clay-rich or fine soils, but there's obvious problems in steep areas, which we have a lot of. I'm going to switch gears now to some of our restoration work and talk about one of our major restoration projects up in the Hollow Tree watershed. This is in the northern portion of MRC's ownership. It's Hollow Tree is a tributary to the South Fork Eel near Leggett, California. It's one of the few watersheds that has a consistent presence. Most of our watersheds are dominated by steelhead and coho, as well as other fisheries. Hollow Tree is 303 delisted for sediment and temperature. We implement this project by utilizing Trout Unlimited and Pacific Watershed Associates to apply for Fish and Game grants, where Trout Unlimited, the applicant, and Pacific Watershed Associates does all of the assessment and implementation grant writing and oversees the actual projects. This relationship was originally developed down in the Garcia way back in 1998, and then we transferred the whole system up to Hollow Tree. So the first phase in Hollow Tree restoration started in 2003, and by the end of phase 6, which is projected to be the end of 2013, the total project cost will be around $4.2 million, $2.9 million coming from Fish and Game and $1 million from MRC. 187 miles will have been assessed, and 126 miles will have been treated by then. The difference being that some of these roads that were assessed were treated during timber harvest plans, and those almost 10 years of work, and as well as some of the road segments were deemed more potential damage than good. Example being decommissioning a road segment that's right next to a water course may cause more erosion than the actual implementation of the restoration project, so we decided to forego those segments. Here's a photo from one of our culvert to bridge replacement projects up in Hollow Tree on Walters Creek. This is a pretty typical situation where we have a class 1 barrier. We take out the old pipe and put in a bridge. Some of the totals from the Hollow Tree project by the end of phase 6, projected to be 2013, we will have treated 641 stream crossings. 325 of those will be decommissioned. Over 3 miles of habitat will be opened or improved for salmonids. The whole project will have created roughly 84 jobs. The main contractor on that job is Ed Curdi out of Fort Bragg. He's done a wonderful job, him and his crew. But one of the tools that we use in planning out these restoration projects is a software package developed out of British Columbia called Softree. I mainly use this software when working on fish passage barrier projects. I basically go out and survey the site with a clinometer, compass, and a measuring tape, and I can get some real rough measurements of the topography, plug it into the software. I can even do some little 3D modeling, generate a surface, and then we can tinker around with designing a culvert removal project to put in a bridge, and we can get an estimate of cut and fills and post-design slopes. So it's a very useful tool. Fish passage barriers are a major issue on the property, but as I said earlier, we have fixed most of the obvious ones. Since 1998, we've fixed approximately 35 barriers and up or improved over 20 miles of Class 1 habitat. One of the examples of these projects is on John Smith Creek, which is a tributary to the North Fork Navarro. This was an undersized pipe that was a partial barrier to fish passage. This project was implemented back in 2003. It was deemed that adults could pass through it at high flows, but it was impassable for juveniles. So here's some of the thought process that we go through when planning out these fish passage barrier projects. So we identify a Class 1 barrier, and then we do the hydrologic calculation to see if the pipe is undersized. Any pipes that size out larger than 6 feet, we typically default to a bridge. We actually don't install too many embedded culverts. So once we decide that we want to put in a bridge, we start looking around for cheap rail cars. That's our preferred bridge surface. There aren't too many cheap rail cars left, so we're starting to look at other options. Then we start thinking about bridge abutments, and there's a lot of road segments out on MRC property that have very large fills on them. So if you don't want to create really steep approaches to your bridge or create a through cut, you have to build some pretty large bridge abutments. And in the past, we've mainly driven pilings. That's been the default bridge abutment. You can span about 70 feet with a rail car bridge, but you need to put in abutments to support the ends if you have very large fills. And on John Smith Creek, we had a pretty large span to make, and we were able to drive pilings. So what's happened between 2002 and roughly 2010 is that some of the permitting issues have changed, mainly on grant projects, and we were unable to drive pilings on a project in 2010, so we had to look at some alternative bridge abutments. And we found a technology out of Colorado called GCS walls, and these are geosynthetically confined soil walls. Basically, you build 8-inch lifts using road fabric, carefully compacted rock and soil, and cinder blocks, just your standard construction cinder blocks. It's a very affordable technology. It does require a lot of labor, but you can build very tall walls to 50 feet tall. Here's an example of a finished product at Little Jack Creek. Note that the cinder blocks do not provide any structural support. They're mainly helpful at reducing erosion around the face of the walls and rolling out the fabric for your lifts. They can the fabric and you can roll it back easy, but we're really happy with this technology. So another major issue on the landscape is hydrologic connectivity. Approximately 370 miles of roads are within riparian areas, and 20% of these roads are no longer in use. They're decommissioned or historic. So we want to monitor for hydrologic connectivity and road surface erosion. And one of our monitoring programs, one of our many monitoring programs, is road surface erosion monitoring. We're implementing this out in one of our focus watersheds in the South Fork Albion. And it's based on Chris Surfleet's work at Oregon State University. We're currently monitoring about 20 sites in the South Fork Albion watershed. And the basic idea is we install these roadside flumes that capture a certain area of that road segment. We go out in the wintertime during high storm flows and collect grab samples at the outlet of the flumes. We have Odyssey capacitance water level loggers. These are devices that are made in New Zealand that collect and log the water level within a standpipe. Those are going all winter long, and then we download those at the end of the year. And then we create some relationships between discharge and suspended sediment, and as you can see on the graph, these relationships that we have aren't exactly what we're looking for in terms of accuracy. This is mainly due to the fact that we're not collecting turbidity measurements, so we're hoping to maybe improve our accuracy with a higher sampling frequency, or maybe actually using some turbidimeters in the future. But the overall goal of the road surface erosion monitoring is to establish a watershed scale suspended sediment load for the focus watersheds, and then extrapolate that to the entire property, as well as comparing results from the current model that we use for surface erosion, which is SED model. I've noted that the connectivity at each site is highly variable. Some sites deliver every storm and some never deliver, mainly due to the fact that our heavy equipment operators have done a great job of disconnecting the site from the watercourse. And as I said earlier, those diverted springs and watercourses are a major issue. So that's the end of my presentation. I wanted to thank Richard Harris and his crew for inviting me.